I'm very pleased to welcome Céline Peroux, who is talking about the cosmic baryon and metal cycles. She is the first in a series of this semester, so it's an honor. And Patrick is going to introduce her. So the colloquium is for 45 minutes, and it will be followed by questions and comments by the audience. So Patrick, I give you the floor or the screens and to introduce Céline.
Okay. I'm a bit annoyed to introduce Céline Peroux in English because if you go to the web page of Céline, you will first find a beautiful text written by Victor Hugo. And I would not dare translate Victor Hugo in English. But the text says somewhere that human spirit produced 3 keys that open everything. These keys are numbers, letters, and musical notes. If I had to find a number, I would say that in 2000, Céline was in the middle of her PhD at the Institute of Astronomy in Cambridge, UK. If I had to find letters, I would say that Céline has spent quite a bit of time at ESO, Garching. She was an ESO fellow from 2003 to 2006, after being a Marie Curie fellow at the Observatory Astronomico di Trieste, and just before being hired as a chargé de recherche by CNRS in the Laboratoire d'Astrophysique de Marseille. And she is currently back to ESO as the project scientist of HIRES, the high resolution spectrograph to be mounted on the ELT. And I guess that everybody knows that this is the most important instrument to be mounted on the ELT. And finally, if I had to find the musical notes, I would say that Céline is a leading expert in the field of absorption line systems, especially Lyman limit systems and damped Lyman alpha systems and their relation to galaxies. She is mostly interested in the cosmic cycle of baryons and metals. She managed an INR project called the History of Baryons, Intergalactic Medium and Galaxies Coevolution. And she recently led a review published in Annual Review of Astronomy and Astrophysics, the cosmic baryon and the metal cycles. And this is about these cosmic cycles of baryons and metals that she will talk today. So Céline, please.
Thank you very much, Patrick. Thanks for having me. I wish I could have traveled to Paris and meet you all in person, but I'm glad that we can at least interact and talk about science together. Thank you for saying a few words. Patrick and I share, of course, a lot of overlapping interests in studying the gas around galaxies across those years, and using high-resolution spectroscopy amongst other tools to look for this coevolution between galaxies and gas. And indeed, as Pierre has mentioned, I realize that I'm the first to talk here at EAP for this semester. And perhaps some of these topics that I will cover are related to some further colloquia that you will have in later. I realize that Roberto De Carli and Linda Tacconi are also invited and will cover some of the aspects of the molecular gas content of galaxy in particular, and its global evolution with cosmic time. So I think this is an interesting connection between these different works. So let me first start perhaps with this diagram showing the different components in the universe. Most of you know that dark energy and dark matter are the major constituents in the universe. And they are the topic of many studies, both observational and theoretical. They are very exciting missions in particular, trying to probe the nature and the global content of this component. But today I'm going to concentrate on the so-called normal matter, the baryonic matter. And in fact, I'm going to argue that even this is poorly understood to some level, because only 10% of the baryons are produced by starlight that make the galaxies. And the remaining majority of the baryons are in form of gas that emits very little light and is very difficult to observe with direct emission. And this is mostly the topic of what I'm going to talk about next. So let me start with this simulation of a galaxy by TNG50 that shows how galaxies are fed by gas from the cosmic web. This gas is first ionized, then cools down into atomic form, and then further down through Lyman alpha radiation into molecular gas. That is the fuel for star formation. These star formation processes will drive galactic winds through AGN and supernovae that in turn are going to pollute the surrounding medium in metals, as shown here in this blue color map. And this in and out are moving with velocity of the order of hundreds of kilometers per second. But again, the stars, as traced by H alpha, only capture a minute, a small fraction of all of these processes. And so these processes of gas moving in, being transformed and moving out of galaxy is what I call the baryon cycle. Let me perhaps start by highlighting some of these properties of the gas. Here in the middle, I'm showing a galaxy at redshift 2 that is going to evolve into a Milky Way at redshift 0 that has been simulated by INZO, that is the simulations that have enhanced resolution in the halos of galaxies. And I have color-coded the gas according to this column density, which is essentially the number of atoms along the line of sight. And the color scale on the left shows you the denser gas in green moving down to the lower density gas in blue. The top left panel shows the column density distribution of these different absorbers. So this is the number of absorbers of a given column density. And we see for H1 atomic gas and for H2 molecular gas that there are fewer higher column density systems in the universe. The top right panel shows the relation between this column density, which is an observable, and the actual volumic density expressed as a cubic centimeter. And again, the higher the column density, the denser the gas, the lower the column density, the lower the density itself of the gas. The right bottom panel shows the relation between the amount of gas that is neutral and this density. And at high density, the gas is mostly neutral, but as we move towards lower densities, then some of the gas starts to become ionized by UV background. And the bottom left panel, I'm showing the distribution of gas in atomic and molecular form around galaxies, right? So this is now the column density as a function of radius of a galaxy. This is, again, illustrates TNG results. And you see immediately that H2 dominates only at very small impact parameter, at very small radii in the center of galaxies. And H1 extends further, but the column density decreases. So essentially, the high density objects are rare. Now, how do we probe this gas with observation? I mentioned that the emission from this gas is not strong. So we revert to an approach that is based on absorption. That is, we use an unrelated bright background source, let it be a quasar, a GRB, a FRB, and we look at, in the spectrum, all of the gas that is absorbed by these photons that are emitting in the background source. So here at the top, I'm showing an image of the structures that this line of sight goes through. Some of this is associated with denser region in the universe. Some are more associated with voids in the cosmic web. And the bottom panel shows the spectrum of a background source. Here it's a quasar. This is a super high resolution UV spectrum of a bright quasar with high signal to noise. So the emission lines here are intrinsic to the quasar properties. And the many absorption lines that one sees are not noise, they are truly the signature of gas along the line of sight to the quasar. To the left of the Lyman alpha emission, we see many Lyman alpha absorptions that we call the forests that compose of many smaller objects. And they are associated with this Lyman alpha multiple metal lines, as shown on the red part of a spectrum. This absorption technique is very powerful. It's very direct, simple. We are counting the number of atoms or the number of molecules for that matter, and we can derive information on the temperature of the gas, of its metal content, etc. Very importantly, this technique allows to reach densities that are difficult to probe otherwise. And not only that, but it does this independent of redshift. So the sensitivity of the observation depends on the brightness of the background source. So if you have high enough, bright enough source at high redshift, you are as sensitive as you are at low redshift. So this is a very powerful way to probe the gas in the universe. Now, this gas, as I say, is a fuel for star formation. So let me go back to what we know about the cosmic evolution of star formation history. You're very familiar with this plot from Madden and Dickinson, that shows that starting from high redshift, stars are being formed to reach a maximum around redshift 2, the epoch of galaxy assembly. And then there's this dramatic decrease by an order of magnitude in the star formation rate, which is counterintuitive. You would expect that the more stars are formed, the more the star formation evolves with redshift. And one of the main questions today in extragalactic astronomy is to understand what makes this decrease in the star formation rate history. So let me go back to the previous phase of the baryons, to the atomic gas. I think we have now made very accurate measurements of the H1 content of the universe. I'm showing here a type of plot that I'm going to show several times, that is plotting the mass density. So this is the y-axis, and the left is in a unitless quantity, and the right, it's in units of solar masses per cubic megaparsecs. So this is the quantity of neutral gas that is measured at low redshift from 21 centimeter radio emission, and at higher redshift from these quasar absorbers that I've just talked about. And I think this quantity is now well constrained. It's evolving very little over time. And I think it's interesting to compare the evolution of the atomic gas with the star formation. And this is the inset here on the top, where I'm plotting the rate of change between this quantity at redshift 5 and a given redshift. And you see that the H1 evolves not as quick as the rate at which we are making stars. And those two lines cross over just above redshift 2. So we are not consuming enough H1 to make all the stars that we see today. The next step, of course, to this star formation processes is to look at a phase that is closer to star formation, and that's molecular hydrogen. Molecular hydrogen has very recently, especially with IRIME and ALMA, been probed in a cosmological way, in a very looking at the global content of H2 using CO as a proxy, of course. And I'm showing here a number of so-called blind surveys, so looking blindly across fields to quantify the amount of molecular hydrogen in the universe. In PIC in particular, I'd like to highlight some work from ALMA-Cal. ALMA-Cal, as you know, is a survey that makes use of ALMA calibrators. So ALMA is spending up to 20% of its time on its amplitude and phase calibrator. And those happen to be bright millimeter sources, quasars, that one can use to do similar studies as those blind surveys. But then this is spread over the whole sky. So it allows to address issues related to just having deep field in small area and address the issue of cosmic baryons. But to say those results, I think, are still in their infancy because there's lots of new understanding of which alpha conversion factor between H2 and CO needs to be used. However, what we see is plotted here. So this is again the omega plot, the mass density plot. I've plotted here on the top in blue the total amount of baryons. We know that very well from both anisotropy in the cosmic microwave background, from Big Bang nucleosynthesis, deuterium, and also more recently from dispersion measurements towards fast radio bursts. And all of these results agree to this value of the total amount of baryons. Now, most of the baryons in the universe are in ionized form that are not probed with the observations I'm talking about. Here, I'm concentrated on the phase that is near to the star formation, and that's the neutral gas that is shown here again in green. This is the fit to the data I was showing earlier. And in black here, the molecular phase. In pink, you have the stars again. So immediately, one can see that the molecular gas also, so much like the star formation rate history, increase from high redshift to reach a peak and then decrease towards the low redshift. Now, another interesting point I'd like to stress is that the neutral gas dominates over molecular gas at all redshifts. So this is independent of galaxies. I'm looking at the total amount of gas in the universe, and there is more H1 than H2 at any redshift. I like this plot very much, but it may be a bit complex. So let me try to walk you through this. This is essentially the same information, but now plotted in a cumulative manner. So again, the same color coding. The gray is for molecular gas, the green is for atomic gas, and the pink is for stars. And I have plotted as a black dotted line the amount of this so-called condensed matter Observatory 6 and how it would look like if it were not evolving. But it is evolving, right? So we see that molecular gas decreases it's making, as H1 is decreasing because H2 is made of H1. But yet again, there are more stars being formed than the gas that has been depleted. So the question is, how do the baryons cycle through these different phases? And to answer that question, I think it's interesting to look at the time scales. So here I'm showing the depletion time scales, which essentially is the time scale it takes for the gas to convert into stars. And in particular here in gray, I'm showing the molecular gas depletion time scale that we derive from both H2 and SFR measurements. So again, those are global measurements. They can be directly compared with work from Tacconi's group that are shown here as a black line up to Redshift 2. So those are dedicated observation of targeted massive galaxy up to Redshift 2. And those two measurements are much alike. In fact, there's very little evolution of the H2 depletion time scale over time, which I think is suggesting that there is something universal about the physical processes of conversion of molecular gas into stars. So these observables, in turn, allow us to ask the following questions. I make more stars and I consume gas. How much more gas do I need to input into the system to explain the amount of stars that are being formed? And this is shown here as a purple solid line at the bottom of this plot. This is the rate density, the net accretion rate density that I need to input into the system to make all of the stars that we see today. This quantity is inferred from the observation, and it captures both the motion of a gas coming from the IGM into the ISM, but also the transformation of a gas from ionized to neutral and hence molecular. And what we see is that it's pretty flat and then decrease at low redshift. I think it's very interesting that if we compare the shape of this curve to expectation from the halo baryon accretion shown here in black, we see that by scaling to a 4% efficiency, we can pretty much reproduce the net accretion rate that our observation derive. So this is telling us that essentially the decrease in star formation rate at low redshift is related to a lack of gas. The gas reservoir is just drawn, and there is not enough gas to make the star anymore. And this is very much in line with the bath tube or regulator model that describe galaxies as slowly evolving equilibrium system, right? So you have inflow, outflow, star formation. So at early times, this gas accumulation, the star formation rate is limited by the gas reservoir. And at a later time, it reached a steady state in which the star formation itself is now regulated by this net accretion rate. Now, a somewhat related question, of course, is what are the metals doing in these systems? So again, I'd like to stress that here I'm talking about metals being anything heavier than helium. And so there are the metals that are made in stars within galaxies. So you may recall that some 20 years back, there was a question posed by Max Bettini and other collaborators that noted that the expected amount of metals that one could derive from, again, star formation rate and the yield of metal production due to different type of stars, and the accounting of all the contributor to metals. And indeed, at that time, at Redshift 2, Lyman break galaxies and DLAs will show 1/4 of the expected amount of metals. So in this review, we've revisited that problem with newer data. But first, I would like to tell you a few words about how metals are distributed around galaxies. And again, I'm going to revert to simulation here, in particular illustrious TNG50, showing one example here of a galaxy. The blue panel is showing the metallicity map around this galaxy. And the right panel is the gas velocity, where negative velocity in green are gas moving in, and positive velocity in red are gas moving out. And so what we see is that metals are not distributed uniformly around galaxies in those simulations. And in fact, the intake, the gas that is inputted into the galaxies is much more metal poor, and the gas that is outflowing naturally is being enriched by star formation is more metal rich. And I'd like to point your attention to this azimuthal angle that we define as the angle between the major axis of galaxies and the minor axis. We've looked at a sample of galaxies in illustrious TNG50, and we've realized that the gas metallicity shown here on the y-axis is correlated to the gas radial velocity, where again, statistically speaking, the gas inflowing into galaxies is more metal poor than gas that is outflowing. And this is also a function of this azimuthal angle. So there's a geometrical effect where inflows is more likely to take place along the disks of galaxies, and outflow just use the minor axis because this is a path of least resistance, essentially. Now we can look at observable in particular, and I'm showing here the relation of gas metallicity again. I should stress that gas metallicity that I'm plotting here as with respect to solar metallicity. So 0 is solar metallicity, -1 is a 10th solar, -2 is 100 solar. So this gas is quite poor in metals, but there is enrichment of metals in this gas as a function of azimuthal angle, whereas there are more metals along the minor axis. And I'd like to stress that this is true for both TNG50, but also EAGLE, that are two different cosmological simulations that have different numerical and physical models, different UV backgrounds, and different numerical solutions to these problems. So hence, if we, despite the complexities that the movie I've shown at the beginning of processes of gas moving in and out and maybe recycling and falling back, there's a net effect of metallicity with azimuthal angle. I think this is a very important result from simulation that we need to confirm with observation. Now, let me talk more globally about metals. So we can use quasar observer to compute the amount of metals in the universe. I'm showing here in green individual measurements, and in black, they are the H1 weighted measurements. I'd like to stress that our current observations are way above the detection limits that I have shown here as horizontal lines at UV and optical wavelengths, right? So there is pristine gas, but it's very rare. We find, again, a mild evolution of metals. I'd like to stress that this metallicity have been corrected for dust depletion using Ed Jenkins and Anna Shia methods that is empirically based on Milky Way and magic clouds methods. And these measurements of metallicity combined with the mass of atomic gas in those systems allow us to look at the metal mass density. So again, same color coding here in green are for gas that is mostly neutral. In purple is partially ionized gas, and in blue is ionized gas. So our measurements are robust and complete only for some redshift for the lower color density systems. But for neutral gas, we see most of the metal up to redshift 5. And in fact, this dominates at all redshifts again. Now, how does it compare with the expected amount of metals? This is again a computation by looking at the total metal production by star formation by integrating essentially the star formation rate density with a return fraction factor R. Much to my surprise, this result indicates that at redshift 3 to 4, most of the metals that we expect are in the neutral phase. I find that very puzzling. So we looked at this in simulations again. This is a busy plot, but essentially I'm showing again in green the neutral gas metal density of the densest gas. And on the left column, there are two flavors of a semi-identical model called Galaxies that is trying to reproduce this amount of metals. And on the right column, top is the Eagle results and bottom is the TNG 100 results. And it's interesting to note that most of the simulations do not find as many metals in neutral gas as observed at redshift 3. TNG 100 may do so, but the black here is indicating the total amount of metals. The data points are observables and the lines are the model. And you see that TNG 100 is higher. The total amount of metals predicted is higher than observed. So there is a mismatch here. So in this work that we've just put on astrophysics yesterday, we've remained puzzled about how come none of these simulations managed to reproduce the observed quantity of metals. And I think this is a topic of investigation that remains open. Now, let me look at other phases of the baryons. Of course, we've measured the amount of metal in stars. They are shown here at low redshift in pink, and also in the hot gas up to redshift 0.7, and this is shown here in yellow. So this is hot gas in inter-cluster medium and inter-group medium. So this is measured at X-ray wavelength. Now, how does this global amount of metal look like? Here I've made 4 pie diagrams for 4 different redshift ranges. Let me start at the bottom right. This is at high redshift. As I say, most of the metals that are expected are found in the neutral phase. At redshift 3, the bottom left panel, the other lower density gas is contributing some fraction of the expected amount of metals. At very low redshift, this is the top left panel, there are more contributors. Half of the metals are in stars, and a good fraction is in hot gas. But at intermediate redshift, at 1.5, we have not yet measured the amount of metals in stars or in a hot gas. So, we don't, this gray area just represents the lack of direct measurements, but we are suspicious that most of the metal will be in those phases. And I think, measurements with Athena and other X-ray facilities in particular will tell us about the amount of metals in hot gas. So taken together, today there's no strong evidence of a missing metals problem, because we have either observed the metals we expect to see, or we know where we think we would see such metals. So let me now move to a connected phase of a baryon, which is the dusts, which is the solid phase material that compose the metal. It's very important to look at the dust's mass in the universe, because this is critical again to star formation. It's where the molecules are formed. but also it's important, potentially biased into our measurements of a property of galaxy at high redshift. And that's where, millimeter observations, of course, provide new clues about dust obscured star formation, for example. So as I say, when we've measured the metallicity measurements of quasar observers, we've corrected for dust depletion. Now we can use in turn this correction to estimate the column density of dust in these systems. And when we do that, we can then derive a dust to gas ratio. So this is shown here on the top panel. This is the fraction of interstellar mass incorporated into dusts as a function of metallicity. I'm showing here as points the quasar observer measurements for different redshifts. The color coding is for redshifts. The blue line is the maximum dust to gas ratio. So all of the metals are in dust. The red cross is the value for the Milky Way, and in black, I've shown some recent results from measurements of DTG in local galaxies. And what we see is that this relation between dust to gas ratio and metallicity that is observed at redshift 0 is also seen at higher redshift, but somehow at some lower metallicity, where our measurements probe also this DTG, there is a larger scatter. At the bottom, I'm showing the dust to metal ratios. This is a fraction of all the metals mass bound into dust grain. Again, the black is indicating the Milky Way DTM. And there is again a trend with metallicity, with even larger scatter that I think is reflecting the complex dust chemistry at play. Now, how does that redshift evolution look like? Again, here is the dust to gas ratio as a function of redshift for individual measurements in pink and for H1 weighted measurements in red. Now, I'm going to give you one more reason why this kind of study is important, is that, again, we can turn this estimate of dust in the systems combined with the mass of H1 gas to derive the dust density in the system. And I'm showing here these quantities that we've measured up to redshift 5, and we can compare this dust mass density with other measurements that have been made at lower redshift, for example, using extinction or reddening of background quasar in magnesium-2 system in the Sloan survey, or spectral energy distribution fit of large galaxy surveys, including gamma and so forth. And those are shown in different colors here. So where those measurements overlap, the argument is good, but of course, our new measurements extend to much higher redshift. I like also to contrast those observable with the far infrared background that provides, so these are Herschel measurements, and that provide a total quantity of dust that is above measurements in galaxies. And we looked at these newer models that include treatment of dust on the fly. So on the fly dust tracking in cosmological models are now possible. I'm showing two examples of this from Gadget 3 in solid line and from Gizmo Simba simulation as dashed line. And both those simulations, are offset in normalization, but they have this similar shape of increasing mass density of dust with a plateau and then again a decrease. And I think this remains to be explained because the lowest redshift evolution indicates that there is more dust being destroyed than produced. And we've looked at this a bit more carefully with Andrea Ferreira and looked at the budget of dust production and dust destruction between redshift 1 and redshift 0. And I'm showing here in terms of dust mass density, the different contributors that we can estimate. And our study indicates that likely the mass destroyed by supernovae events is overestimated. And we believe that we would need a factor of 5 to 10 less dust might be destroyed to explain the observable. Again, I think this is a very interesting topic that would need to be looked at in more details. Now, I've talked a lot about global quantities, baryon and metal cycles over large cosmic times. Let me now try and zoom in closer to galaxy and try and probe the galactic baryon cycle and witness directly this transformation of gas and metals that I've been talking about with the help of observations. I think in recent years, there's been a excellent progress in combining these probes of gas I've been talking about with more traditional probes of galaxy through emissions and understanding the metal content both in gas and in ISM of galaxy, the geometry and the kinematics. And that's in particular driven, I believe, by new technological development, including 3D spectroscopy, which is essentially an image where every pixel is also a spectrum. And I think a true game changer in that field has been the MUSE instrument and the VLT that probes the galaxy responsible for the absorption we've been studying in great details. There's been a number of surveys trying to combine this different approach. I'd like to say a few words about our efforts that we call MUSE ALMA Halos. That is unique in the sense that it's a multi-facility campaign that will use quasar absorption spectroscopy to probe the neutral gas, MUSE data to probe the galaxy associated with those gas and the ionized form of the gas, ALMA to look for the molecular content of these CGN regions, and of course, HST through a 40-orbit medium program that has just been completed to study the stellar component of these objects. So I'd like to highlight in particular some great work from Simon Wang, who's my current PhD student here at ESO. So let me give you one example of the type of things that we are seeing. Here is a field that has been observed with HST in broadband imaging and with MUSE. I'm showing here on the right the white light image. It has a large H1 quasar observers that has a low metallicity at redshift 0.3. Now, we can use MUSE as a pseudo narrowband filter and look at all the galaxies that are at the redshift of the observer. And it's surprising to see that we find up to 11 galaxies, including very low impact parameter objects, so objects that are very close to the quasar sightline, that one will not see in imaging alone. But thanks to the 3D spectroscopy, we can disentangle the contribution from the quasar and the contribution from the intervening low brightness galaxy in front of the quasar. In fact, we can also observe this kind of fields with ALMA, which can be thought of as an IFU. And here I'm showing in particular a detection of CO120 in 3 of the objects that have been detected in MUSE. I'd like to stress that band-free ALMA observation very nicely match the MUSE field of view. The primary beam is quite similar to the is 1 arc minute, very much like MUSE. And also the combination of those 2 observations allow to disentangle ALMA single line degeneracy. So we have other emission lines in our ALMA cube, but thanks to the MUSE information, we know what's the redshift of those lines. Now I'm going to try and give you a better sense of the amount of information we have in this data by showing a little movie of this field, where again, I have cut the wavelength frequency to cover the expected detection of oxygen-3 on the left and CO120 on the right. I have removed the quasars. It's shown as a white square in the plane of the sky. And so you see here, the image on the sky and the depth of those cubes. Cones are frequency or wavelength. And so, a little blob is an emission only detection, and a cone, represents an object that is detected in continuum. So I was once asked this, so I would stress that I have not, these are real data coming from our observatories. Of course, the MUSE is squared because this is the shape of our detector. ALMA is round because we are doing interferometry and Fourier transforming it. And in fact, there is no clear cut in the primary beam, it's actually the position at which the signal to noise increases significantly, so that detections are less reliable. And this is what you see here on the right, this noisy pattern. But in fact, there is information beyond this as well, I'd like to stress. So here I'm rotating this, and you see those multiple objects that I've mentioned earlier. In Muse on the left, you see a number of them are detected in continuum. You see 3 blobs along those continuums, so those 2 or 3 lines and each beta. And of course, we can zoom in and look carefully at these objects, and you see that there's structure, right? There's velocity information in both molecular and ionized gas that we can kinematically model to understand the connection between this gas and the one that we've probed in absorption, just using the chance alignment of the background quasars. There's an enormous amount of information, so I'd like to highlight in particular the kind of results that we have from such studies. I'm showing here on the top the velocity field of galaxies that we've been observing with Muse, and we have a forward model in 3D space, the velocity field of that object, and extended it to the position of a background quasar. So here the red indicates positive velocities, the blue are negative velocity, the black here is the change alignment of the background quasar on this data. And what we see is that the emission signature happens around 100 kilometers per second. Now we can compare this to the spectrum of a background quasar. Indeed, there's a strong feature precisely at this velocity that is, evidently associated with a disk rotation. Now there is another component that is kinematically distinct and that cannot correspond to this rotation. This component also happen to be more metal poor, and thanks to angular momentum arguments, we think this is a signature of gas accretion. So this is very important because I've talked globally about the need of gas accretion into galaxy to explain star formation rate, but finding direct observational evidence for accretion is challenging. So here is the mental picture I've been drawing of this system. So if we go back to M81, M82 group that we observe at optical wavelength, we see very distinct objects. Now, if you look at this at radio wavelength, we see evidence of extended low density, low surface brightness H1 gas that is the remnant of interaction between those objects tidal stream. And if we zoom in onto M82 in particular, we have a school case example of galactic wind. So I think what those quasar observers, probing low density gas are showing us is all the complexity of this physics that we have a hard time capturing from starlight observed at optical wavelength. Now, with the few minutes I have left, I'd like to highlight 2 other avenues that I think will be developing in the future. One is to reach advanced information on the spatial scale. So clearly, this background quasar are one line of sight. It's a pencil beam. So the information we have is limiting spatially. And I think there's a lot of prospect of detecting low surface brightness signal in emissions that will provide more information about the mapping of this gas. But meanwhile, there are a few tricks that one can play. And in particular, we think there's a lot of clumpiness in the circumgalactic medium, in the gas around galaxy, with possibly evidence of metal poor mixing and shattering. So the idea of having small parsec scale cloudlets of gas that made up together this circumgalactic medium. This is now a foggy simulation from my former student, Ramona Augustin. To probe this observation is very challenging. There's been a lot of efforts using lens background quasar. I'm showing here on the left a sketch of what the idea is to use either multiple image of the same quasar that has been lensed to probe the small scales by using 2 sight lines along the intervening galaxies that are shown here in red. And that provides information on the metal currents length of metals. So it's essentially the idea of what's the metal on larger megaparsec or kiloparsec scales. There's been new work, I think very interesting, using extended arcs to probe the metallicity on smaller scales. But of course, those are very rare and they're not so bright. So what may be interesting in the future with advance in instrumentation related to the ELT in particular is to use extended background galaxies rather than quasar that would provide a background source that is extended for which we can probe all of the absorption over very small scales. And we've started this game with MUSE. Just happen to look at background galaxies that are bright enough at redshift 1.1 to probe foreground galaxies at redshift 1.07. And this is showing you a map of the strength as measured by the equivalent width of a cold gas, 10 to the 4 Kelvin, measured thanks to magnesium 2, and how it varies on very small sub-kiloparsec scale. So we can now probe the inhomogeneity of a CGM thanks to such observation. And because we have information on the current density, we can also derive some information on the upper limit on the mass of the clouds that is believed to be less than 10 to the 9 solar masses. So much of this will expand. We have a MUSE program ongoing to try and have a larger sample of these objects and look at this variation on small scales. Another work I'd like to highlight is the idea to really move to a statistical sample to probe the CGM of galaxies. I love 3D spectroscopy. I think I've made that clear, but I believe that to really have significant sample, we will need to move to multi-object spectroscopy. And of course, there's the foremost instrument coming on VISTA, which is a high multiplexing spectrograph that has a set of different fibers with different spectral resolution. A number of surveys are already planned by the consortium team to look at low resolution at large, highly complete galaxy samples, the WAVES survey and the CRS that are evolution of the gamma survey. But there's a couple of high resolution fibers, 20,000, that we propose to use to look at background quasar in the same field where the galaxies have been observed, right? And we have now asked to look at a sample of almost 1 million background quasar that will be producing 250 absorbers, intervening absorbers that we can now match with 1 million foreground galaxy clusters, AGN, that are part of these consortium surveys. And I'm showing here on the plot the comparison in terms of number of quasar and spectral resolution with other efforts, both ongoing in blue and planned in green. And you can see how our project is increasing both the offered spectral resolution and the number of spectra. So essentially, this is the latest Sloan quasar release, but with 10 times the spectral resolution. And as you know, the spectral resolution linearly scale with the equivalent with sensitivity and hence the number of observers that one can reach. So this is a major step. We are still in the ESO is due to provide outcome on the selection process later this year. We hope we can start this 5-year survey 2 years from now. So please stay tuned. Right, so with this, I'd like to leave you with some take-home messages before I take questions. I think we have found evidence that what drive the shape of a star formation rate history is a lack of the molecular gas, and that's directly related to the net accretion gas rate and the growth of dark matter halos. Similarly, we have found little evidence in a modern census of the so-called missing metals problem. We have been able to measure the amount of dust mass density up to redshift 5, which put new constraint on cosmological simulations. And I think there are efforts of using new multi-wavelength facilities to find evidence of this baryon cycle on galactic scales that are very promising also with future facilities. Thank you very much.
Thank you so much, Céline, for this very nice overview and with a lot of details and information. And I leave the floor open for questions. And Patrick, I leave you to lead the discussion.
So I see a few hands, maybe Henry.
Yes, Céline, thank you very much for the lovely talk. Could I ask you just the really, really simple question? Can you go back to the Maddow-Dickinson plot and then, as an expert, just explain to us what causes the peak and the decrease at high redshift and low redshift now when you put together all of the different things that you've talked about in your presentation? Just to be like 30-second synthetic summary of everything.
All right, so I failed to make that clear, it appears. Let me try that again. So wait a minute. Because I stopped sharing, I lost my keynote, which I'm sure is not too far. Here we are. Okay. Good, so I will share again the Maddow and Dickinson plot. Let me know if you see this.
Yes.
Yes, yes, yes.
So yeah, so this is those processes I was talking about. So, you know, the gas is ionized. I think it's been a great success of cosmological simulation to be able to model a very simple, you know, linear problem, gravity-driven problem of collapse of structure into the cosmic web. So essentially, the density of structure increased with redshift, and this is, you know, in line with the gas cooling down to 100 Kelvin temperature. That is, you know, what's needed to make stars. So as this structure collapse, stars are being made, there are more stars being made, more structure, you know, the structure get denser. And this is, you know, naively we would expect this process to go on, you know, as redshifts evolve. And the decrease that has been observed was challenging to explain. We think this is related to essentially a lack of gas at those redshifts, so that there's, you know, there's a need to have new gas moving in to make those new stars.
Okay, thanks.
Is this answering your question?
Yeah, that's fine. I just wanted to make sure that I understood everything.
Thanks.
Thank you very much for the nice talk.
Thanks, Henry.
Okay, so Siwei has a question.
Yes, thanks, Patrick. And thank you very much for the talk, Céline. So I would like to ask, that is like a question about the TNG simulation, because I've heard that the total gas mass in the TNG simulation actually is kind of like underestimated in the whole like simulation. So I would like to ask, will that impact when you compare like a TNG simulation results with the observation, for example, the H1, H2 gas contribution in the star formation at different redshifts?
Yeah, so let me see if I understand correctly. So when you mean total gas mass, you mean all phases combined?
I think so.
Right, because so just a bit of background. Obviously, you know, again, most of the mass is in ionized forms that I've not been directly talking about. And this is because we have no direct constraint from observation on this phase, but also because I was focusing on the phase that is colder and closer to star formation. As you know, TNG is you know, looking at this mass in post-processing, right? So TNG has cold gas, and then we need to post-process to get atomic versus molecular and so forth. I think it does a pretty good job at H1. is more complex, of course, for H2, which is even cooler, even on smaller scales. And I think the mass in galaxy is fairly well reproduced with TNG. So maybe you refer to the hot gas that we have not directly looked at in this work. And of course, again, our current measurement of the mass of hot gas is limited. Due to observational constraint. I think there is a lot of hopes that Rosita, Athena, Lynx will tell us more about how much of the gas in the CGM region is hot. And I think that would put new constraint on TNG.
Okay, thank you.
Okay, any other question?
Yeah, perhaps, Patrick, I have a question. I mean, one thing that I noted in your very rich presentation, Céline, is the issue of the flow accretion. And you showed a very nice example of a detection of it, but you also said it's very challenging and difficult to observe. Could you expand on this, and what are the future prospects on, I think, this very essential observational issue, and which is in contrast, for instance, to everything that has been done for outflows? Absolutely.
I totally with you here. So, of course, we have a lot of observational evidence of outflows from galaxy spectra, where we see, blue shifted lines in absorption. From, the emission, which is this extended Lyman alpha emission, compared with the UV component of galaxies, both from stacking. This is early work by tidal groups and others, and now, thanks to news in individual galaxies, we see evidence that Lyman alpha is 10 times more extended than the stellar component, which we attribute to as a signature of outflows. And again, we see metals in low density gas, right? In the IGM, we see metal, and these metals have been produced in galaxy. If they end up, several kiloparsec away from galaxies, they have to be expelled. So I think there's a lot of direct and indirect evidence of outflows. However, we need accretion. We need accretion to, explain, as I say, the star formation rate history. We need accretion to reproduce the stellar mass function, and yet this is very challenging to observe. I think that part of it is that it's metal poor. So of course, when we probe outflows with metals, we use that trick. But if gas is metal poor, it's more challenging to observe. I think the velocity involved may be lower. So again, the shift in spectroscopy make it more difficult to kinematically disentangle. And I think the two effects compete. So essentially, my view, and that's what we see in simulation like TNG. I'm talking a lot about TNG because I've worked with this directly, but others, Simba and Eagle and others find the same thing. You see that those two processes compete with each other. And if the velocity involved for outflows are larger, then they overtake, physically, and they are easier to observe. And again, even the cross-section of the accretion may be smaller than the outflow. So the outflow has, conical, outflows, cones that have at large radius a very, very large cross-section. Now, your question, of course, is how can we improve on this? So I do think that we need to work in pairs with simulation. I think 3D spectroscopy, and I'm open here in terms of wavelengths, let it be optical with Muse or millimeter with ALMA. I think the kinematic information is key. It's very time consuming to get, but it's key to understand exactly what the kinematic of a gas is doing. But also I think large samples are required, and that's where maybe, multi-object spectroscopy would help. Because, in absorption, looking at one galaxy intervening in front of a quasar is similar, to probing the mean galaxy property if you look at a large sample of quasar. What I'm saying is that, of course, you're probing one pencil beam information for each galaxy, but if you combine, 100 and 1,000 of these, then you have a mean picture of what the gas is doing in this galaxy. And I think that this will enable us to probe this rarer or more difficult to trace process of gas accretion, which I think we all agree should be there.
Yeah. Thank you. We are on the same line.
It seems.
So I have a question actually. What is your view about the fact that we don't see pristine gas in DLAs? Because at the beginning we could say this is statistics, but people have tried hard to find this gas, and actually, as you pointed out, the limits are okay. We are well above the limits. So what is your view about this?
That's another very good question. I'd like to highlight this is one of the important topic for HIRES. So the idea to look for very pristine gas by having high signal to noise of faint quasar at high redshift. So indeed, there has been an effort of looking for this metal poor gas absorber in a large sample like a Sloan, and this is revealing that some objects are found to be metal poor, but not very many. I am concerned about metal mixing. I think that there may be evidence, again, both in simulation, like in Foggy and others, that the metal is poorly mixed on very small scales. And that means that we are, looking at a very, perhaps kiloparsec or even parsec scale information that may be very different from what we have next door. And so I think this is something we need to investigate. I think it's a very important topic because, again, we would expect that some regions in the universe are not enriched by metals because they have not been close to star formation enough to see those metals. And yet we have very little evidence of this so far.
Mm. But okay, I just say this because, okay, you mentioned mixing, but we just shown very recently that in the Milky Way, the gas is not mixed, contrary to what we thought before. So I think this is really a problem, right? Okay, not to see this pristine gas, because so I agree that this is probably something for HIRES.
So you're referring to work with Annalisa, right?
Yes, yes.
Yeah, I think this is very, very exciting to make this comparison with the Milky Way, where indeed we can have, we could look at much smaller scales. But of course, we are looking at an evolved system, right? So what's happening at redshift 0 may be very different from what happens at redshift 3.
But mixing is probably the same. Physics is the same.
Yeah, but it takes time, right, to mix. So that was my point. But Go ahead.
About your, okay, is that a group? Okay, the system you showed at low redshift, okay, observed with the Muse.
Yeah, so
this is a group?
So, okay, so of course there's an overdensity. So if we look at the redshift distribution of galaxies in the cube, there are more galaxies at that redshift. We've measured the velocity dispersion of a group, and yes, it's consistent. Now, Muse is only 1 arc-minute, so at some point, there may be other numbers further out that we have not observed. But, there is indication more than not that, and this is again, has been surprising to me, that Muse is finding more than 1 galaxy associated to observers. So before, maybe 20 years ago, we had this idea, big, nice NH1, 1 spiral galaxy next to it. That's not what Muse is telling us, right? So not only there is always a galaxy associated with all the observers. I mean, we've worked hard to do that for many years. And now with IFU, we can really see those galaxies, find those galaxies right away. But more often than not, there are more than 1 galaxy.
At which distance, I mean?
Yeah, so this is up to several kiloparsec. But again, I'm making this parallel with M81, M82, right? This gas is very far away from galaxy, and it may be very low density gas that is the remnant of previous merging events or tidal streams. And you see a lot of this. Again, we've looked at this in Ramses, for example. You see a lot of that gas at very low surface brightness that you would not see in emission, or very, very deep, very hard to see in emission with current instrumentation. And so I think there is a hint that this gas is associated with overdensity. Even in ALMA, we find 3 galaxies with CO120. I mean, this is, dense gas that is traced by this large H1.
Okay.
So I think,
I think there is no more questions.
So
we should thank Céline again.
Yeah, so thank you.
Yeah.
Thank you.
And thanks for accepting the invitation for the beautiful talk, and see you at the next colloquium next week. Okay, good.
Great.
Yeah.
See you.
Yeah,
Bye.
bye-bye.
Bye-bye.
See you.